Yeah, all right. So you can see the screen, right?
Yes.
All right. Okay. So last time we were discussing thermal properties and temperature. We discussed how evaporation works, and that's where we talked about the link between temperature, pressure, and volume with each other, right? And with the other properties, for example, temperature was directly related to the kinetic energy of the molecules and so on. So we stopped last time at heat capacities, right? So we'll be discussing thermal capacities. Uh, there are two different types of heat capacities that we can define. One is just called heat capacity, and the other one is specific heat capacity. And we'll see what's the difference is very small, but there is a little difference, right? So let's talk about heat capacity with an example of uh, water inside containers, right? So for example, here you have two different containers and they're at same temperature, right? So suppose it's room temperature, 300 kelvins, and this is also at 300 kelvins. The only difference is that the mass of water inside one of these beakers is more compared to the mass of water inside the other beaker. So you can say that, for example, this is 100 grams of water, whereas this is 1,000 grams of water. So the situation is that you have two beakers, right? They both contain water. The temperature is the same for both of these water, and with different masses. We have 100 grams and the other 1,000 grams of water. And now let's start heating both of these beakers to a same temperature. So I'm going to start heating from 300 kelvins to some other temperature. Uh, you can pick any value. Let's take 60 degrees. So that would be 60 degrees Celsius would be how many kelvins? 333, right? So you just add 273 to any degrees Celsius and it converts to kelvins. Right? So that would be 333 kelvins. Suppose that I want to raise the temperature of my water from 300 to 333 kelvins. Now, the condition is that the you can say the source of heating is the same for both beakers. So for example, if I'm using a heater to heat up these waters, I'm using the same heater for both of these beakers, right? So it's giving same energy and all those other quantities, they are same for both of them. Now, suppose what happens is that it takes about 10 times as long as to heat this beaker, 1,000 grams that contains 1,000 grams of water, compared to this 100 grams of water, right? So this water, 100 grams of water, would heat up quickly compared to this 1,000 grams of water, right? And it kind of makes sense because there is less matter in this beaker, 100 grams of mass, and there's more matter in the 1,000 grams mass beaker. So what this means is that the 1,000 gram water requires 10 times as much heat energy as this 100 grams of water would require to heat it from 300 to 333 kelvins, right? So that's where the idea of heat capacity comes from. we can say something like that this 1,000 grams of water has 10 times more heat capacity than this 100 grams of water, right? So heat capacity is just the amount of thermal or heat energy that I need to raise the temperature by some amount, right? We say by 1 Kelvin, right? Does that make sense?
Yes.
Yes. Right. So it is the amount of heat energy required to raise the temperature by 1 Kelvin. Of any substance, right? So for every other substance will have their own heat capacity. In this case, it was water, and we can have multiple substances for each having their own heat capacities. Now we can work out the mathematics of heat capacity. I think I'll have to go to the next page. Mathematically, I can define my heat capacity by its physical definition, right? That heat capacity is just the thermal energy or heat energy required, right, to cause a change in temperature. And so heat capacity can be labeled as C, right? It's just a symbol that we use, and it's defined as the ratio of the heat energy that is required to raise the temperature, right, by 1 Kelvin. So divided by delta. For temperature, we have been using theta, right? This symbol theta. So this is the heat energy or heat required, and this is the change in temperature. So for any substance, you can calculate its heat capacity provided that you perform an experiment where you figure out how much energy was required to change this temperature, right? So if I divide it by delta theta, whatever this delta theta is, this will give me a number which will tell me the amount of heat energy required to raise the temperature by 1 Kelvin, right? As I'm dividing it by this delta theta. So that gives me some idea also about the units for heat capacity. The units for heat capacity are joules, right, from the heat energy per Kelvin because of this temperature. So these are the SI units. You can also write down it in another units, which is if I'm measuring the temperature in degrees Celsius, so then it will be joules per degree centigrade or degree Celsius. So
which is the SI unit?
yeah,
Which is the SI unit? Is it the first one or the second one?
yeah, these are the SI units, right? In kelvins.
Okay.
Because the SI units for temperature is kelvins, right? Okay, so one a side note really is that so far we have seen that the heat capacity was dependent on one thing. In this example that I gave an example of these beakers, what did the heat capacity depend upon?
Mass.
Mass, right? Exactly. So so for 1,000 grams of mass, it was different than compared to the 100 grams of mass, and that's where the idea of heat capacity came from. So it depends on mass of my substance, or you can say material, right? Exactly in the same way, it also depends on the you can say on the material, right? In simple words, you can say on the material. What material do we have? It's, you can say, the topology of the material, geometry of the material, but more or less just the material where, for example, it's different for water and it would be different for some other substance, for example, copper or gold, right? So the heat capacity depends upon the mass, as we have seen, and it also depends on the nature of the material, or you can just say the material or substance that we are looking at, right? For example, if I take a same mass of copper, right? We used an example for copper. More heat energy would be required to raise the temperature of this copper by 1 Kelvin or 1 degree Celsius compared to any other substance that I have, for example, water, right? So it depends on the materials. For example, water or any other material, for example, aluminum, copper, gold, platinum, and you get the point, right? So copper, aluminum. All right. So now to understand the mathematics of heat capacity a bit more better, let's try to do a problem, an example, and suppose that you have 100 grams of water in a beaker, and you raise the temperature of this. Initially, the beaker was sitting at 30 degrees Celsius, and you raise this temperature from 30 degrees Celsius to 60 degrees Celsius, and you see that the amount of heat that was required to do this thing in lab, you measure it to be uh, so the heat that I have to supply to this is 12,600 joules, right? So if I'm using a heater, that heater should be capable of supplying 12,600 joules to this beaker of water, and it would raise the temperature from 30 to 60 degrees Celsius. The question is, find the heat capacity of this water, right? So what would be the heat capacity of this water? Can just someone volunteer and solve the problem? It's very simple. So again, the situation is we have some mass of water. We're supplying it some heat energy, and that heat energy is capable of raising the temperature from 30 to 60 degrees Celsius. We need to figure out the amount of heat energy that is required to raise the temperature by 1 degree Celsius, right?
420.
It would be how
For
much?
420.
All right. And how did you compute this?
For the formula.
Right. But okay, so using the formula, it's simple, but does the formula make sense, right? Do you understand why is it C is equal to Q by change in temperature, change in theta? Does the formula make sense to you? I mean, there's one thing you can say that, oh, it's the formula, I just put in the values and, write, calculate the answer, and it's simple. But
Yes.
it's something else completely when you also understand what the formula is saying, right? So basically, we just use the physics of heat capacity to write down this ratio, which is defined as the heat capacity, right? So, okay. So this would be then 12,600 joules divided by change in temperature, right? So you have to remember this is change in temperature. So how much the temperature rose? That would be 60 minus 30 degrees Celsius, right? And this would give you 420. It gives 420, right? Yeah, 420 joules per degree Celsius, right? So this time the units for temperature were degrees Celsius. So we just worked it out in degrees Celsius. If in the question they specifically specify to write it down in kelvins, then you can then you're supposed to convert degrees Celsius to kelvins. All right. So now suppose that I add more water to this thing, right? So now suppose it's still the same, everything is the same, but in the beaker, we add more water. And suppose now the water becomes 1,000 grams. What would be the heat capacity of this 1,000 grams of water? You can, there is a very easy way to compute this thing, right?
4,200 because just multiply it by 2.
By 10,
Yes,
right?
10.
Yeah.
Not 2.
Yeah, exactly, right? Because so you can see that because heat capacity is proportional to the mass, so this just means that I can use the ratios or just say that if the mass has increased by 10 times, which is what happened, right? So from 100 grams to 1,000 grams, the increase is 10 times. So that just means that if I multiply my mass by 10, then I'm multiplying my heat capacity by 10 as well, which means that the heat capacity for 1,000 grams of mass would be just 420 joules degrees centigrade into 10, which would be 4,000. So is that clear for everyone?
Yes.
Could you explain the second part again?
Uh, this one the so yeah, so the mass of water has increased by 1,000 increased 2,000 grams, right? So it was initially it was 100 grams, now it has increased to a value of 1,000 grams. That increases 10 times, right? We can clearly see if I multiply 100 by 10, I get 1,000 grams, so the increase is 10 times. We know we have seen that the heat capacity is directly proportional to the mass of whatever material or substance that I'm using. So I can just use this physical knowledge and say that if the mass has increased 10 times, that would mean that the heat capacity should also increase 10 times, right? And so then instead of using the formula, going back and putting in the values, all you can do is figure out how many times did the mass increase. That's 10. Then multiply the heat capacity that you found for the 100 grams of mass and just multiply it by 10 to get the heat capacity for 1,000 grams of mass, right? And so that's just 420 times 10. Clear?
Yeah.
All right. Okay, good. So we don't have more space here. There's just one more thing to this thing, that suppose now you want to compute the heat energy, right? For the same problem, heat energy, what would be the heat energy that I would have to supply to the system to, and again, the system now is 1,000 grams of water, right? Because initially we know the heat energy for that 100 grams of water, but what would it be for 1,000 grams of water if I want to raise the temperature by from 30 to 40 degrees Celsius.
We can rearrange the formula.
Right.
C
So
is equal to
yeah, C is equal to
Q divided by delta temperature or delta.
T. Right. Okay. So all right. So we have C, but the thing is, which C will I use over here?
To 4,200.
Right, exactly, right, because that was the heat capacity for 1,000 grams of water, 4,200 joules per degree centigrade. And the reason that we are using this is because our mass of water is 1,000 grams, right? So this is the heat capacity, and change in temperature is what we have to multiply it with. So 40 minus 30 would give me the change, which is just 10 degrees. So this would be 4,200 joules per degree centigrade into 10, right? 10 just comes from this thing, 40 minus 30 degrees. So degrees Celsius cancels with this thing, and you're left with 42,000 joules, right? So that
Yes.
is the heat energy that I would need to supply to the 1,000 grams of water if I were to raise the temperature from 30 to 40 degrees Celsius. All right. So is that clear for everyone?
Yes, it is clear.
All right. So now let's talk about something more specific, namely the specific heat capacity. And so far we did not make any reference to but how much mass are we talking about when we're raising this temperature, right? So heat capacity was just defined as the amount of heat I need to provide to my system to raise its temperature by 1 degrees or 1 Kelvin, depending on what units you're using. Specific heat capacity is exactly the same thing, right? It is again the amount of heat that is required to raise the temperature by 1 kelvins or degrees centigrade. But this time we give reference to the mass, right? So we'll say that of what, of how much mass. So the amount of heat energy required to raise the temperature by 1 kelvins of a mass of 1 kilograms. Or 1 kilograms is again just an example of the unit. You can say of unit mass, and I'll tell you what I mean by that, of unit mass. So it depends now if the problem statement is using grams as the units for mass, right? So 100 grams, 1,000 grams of mass. In that case, the specific heat capacity would be the amount of heat energy required to raise the temperature by 1 Kelvin of a 1 gram of mass, right? And if it's in kilograms, then you'll use, then it would be 1 kilograms of mass. So that's why we say unit mass, which just means that whatever the unit is, one value of that unit, 1 gram, 1 kilogram, or 1 milligrams or whatever, right? So of unit mass of substance. And that's why it's also called specific. It gets this name specific because it's now talking in terms of the mass of the substance as well, unit mass of the substance. So if we're assigning this just one new variable of unit mass, then mathematically Can you tell me what would be the mathematical expression for the specific heat capacity? I'll use a small c for specific heat capacity, right? So I'll write here, small c. What should be the mathematical expression for specific heat capacity? If you understand the definition of specific heat capacity, then it should be clear.
It is the
It is exactly the same as the heat capacity, but specific to the mass, unit mass of the substance, right? Per unit mass. So I can mathematically say that it is just the heat capacity per unit mass, right? Which is just the amount of energy required, Q, per unit mass to raise the temperature by 1 degrees or 1 Kelvin. So it would be Q by M delta theta, right? Where Q is the heat energy that is required, delta theta is the temperature change as usual, M is the mass of the substance, right? And we prefer to write this mass in kilograms, right? In the equation, we'll use this mass in kilograms. So this means that the SI units for specific heat capacities is just joules per kilograms, and you can multiply with kilograms the units for temperature, which is kelvins, or it can be degrees Celsius. And this expression might be weird to remember, but you can write the same expression in terms of the thermal energy. You can rearrange the equation as Q is equal to mc delta theta. But remember, this C is the specific heat capacity, not the heat capacity, but the specific heat capacity. Right? So any questions from this thing?
no questions.
Okay. So can you tell me if I say that the specific heat capacity, so small c, let's say for water, this value is 4,200 joules per kilograms Kelvin, right? So I'm just making this statement. What do I mean when I say that the specific heat capacity of water is this value? What is this telling me?
It's telling 4,200 to 200 joules is the specific heat capacity per
Exactly.
mass.
Right. But again, in terms of what specific heat capacity is, it's just telling me that I would need 4,200 joules of energy, heat energy, right, to raise the temperature of 1 kilograms of water by 1 Kelvin, right? So that's the amount of energy that I would need. And so these calculations then are very useful in designing, engineering design, your heaters and these kind of things, right? So if the heater's main purpose is to heat water, then you should keep these numbers in mind. Right. So that's clear, I guess, right? Is it clear for everyone?
Yes.
Okay. So Now, finally, we'll end this topic with the different methods of heat transfer, right? And we'll briefly discuss about these methods of heat transfer. You can also refer to these things as thermal processes, right? And the first one that we'll discuss is conduction. Now, it's a method of transferring heat from one medium to another, right? Because you can, and this method is followed mostly in solids and in liquids as well, right? So it is, how can thermal energy, heat energy, be transferred from a solid to liquid, right? So you know that there are you can classify metals in two classes, as in you can classify your elements in two classes, actually more than two classes, but the ones we're looking for is metals and non-metals. And we know that metallic objects are poor conductors of heat, right? And what does that mean? We say that these wood, for example, is an insulator.
It
What does
means
that mean?
it means it is hard to absorb. For it is hard to absorb heat.
Right,
No,
exactly. So it it's a poor conductor of heat. It conducts heat poorly. So it's difficult to use, for example, a poor conductor for transferring heat. It would be a poor conductor. It would not be efficient. The heat would be lost in the environment rather than being conducted from this poor conductor, or poor material, a non-metal. Because as a non-metal would, you heat a non-metal, what you do is the molecules will vibrate, right? They'll vibrate and they'll cause the, for example, if I draw something like this here, if I heat this material, what happens is that the molecules are going to start moving more and more, vibrate more. And if one molecule vibrates more, it's going to transfer its energy to the adjacent molecules sitting next to it, and they're going to vibrate more. And so the energy would be transferred from a hotter part of the material to the cooler part of the material. It just happens so that in non-metals, it's difficult for this heat energy to just stay in between these atoms. The energy is lost to the environment as well, and then that's why they are poor conductors of heat. For example, on the other hand, for metals, this heat remains mostly in the material, and it is transferred from this. So for example, if this atom was vibrating, it will transfer it to this atom, then it will transfer it to this, and until the entire material and made up of these molecules, they start vibrating more than before, the energy will not just go into the environment. The energy will make sure that first all these atoms or molecules start vibrating more, and then it will leave to the environment. For, while in the case of non-metals, the energy is dissipated into the environment quickly. So that's